now. So let's start with Bernoulli sequences. So Bernoulli sequences describe a sequence of repeated trials. So what does this mean? Right? It means that each trial must result in a success or failure. So there's a few different ways to think about this, right? It means that we must have um, kind of two outcomes, a success or a failure, right? An example of this might be if you are going to work in the morning, and it's really cold, and you have an old car or something like that, and you're trying to get your car to start, um, and every time you try to get your car to start is a trial. Maybe you try 3 times for your car to start, right? And you have a success, which is your car starting, or a failure, which is your car not starting, right? This can also get more complicated. So instead of just thinking of kind of this two outcomes, right? Sometimes you even need to broaden it a little bit. So an example of this might be if you have the classic example of a bag of magnets, and you have, say, 5 different colors of magnets of marbles. Sorry, marbles. 5 different colors of marbles in there. And you're asked, what is the probability of pulling out a red marble, right? So even though there's 5 possible outcomes, because you could pull out 5 possible colors, right? You still have a success, which is pulling out a red marble, or a failure, which is pulling out any other color. So you also need to consider that when you're thinking about what is a Bernoulli sequence. Our next rule is that the probability of success is constant for all trials, right? So this means that the probability of succeeding doesn't change. An example of this might be if we're going back to our starting our car example. If, for example, maybe your car is more likely to start the more times you try to start it, because it's kind of warming up each time you start it, or something along those lines, that means that we wouldn't have a Bernoulli sequence, because the probability of success of the car starting is not constant for each of the trials. It's changing, right? Our last rule is that the trials are independent. This is really important too. It means that a previous trial is not impacting the following trial. The classic example of this is, again, if we have our bag of marbles. If you're pulling out 3 marbles, right, but you're not putting them back in every single time you pull one out, the probability of pulling out each color is changing. So say you pull out a red marble to begin with and you put it down, you don't put it back in, there's now less red marbles, or a smaller proportion of red marbles and a larger proportion of other colors of marbles compared to your first trial. So now you have a smaller chance of pulling out a red marble again. So this means that our trials are not independent. So independent trials are always going to have what we call replacement, which means every time you kind of, take something out, like a marble or a card out of a deck or something along those lines, you're always putting it back in, right? The one kind of caveat to this is when you are looking at, I guess, kind of continuous random variables in conjunction with Bernoulli sequences, right? So sometimes, and again, these are the complex questions, so like I'm not going to be going over this too much today, but just kind of if you are like more of a a determined student, you might want to look into this yourself. If you're looking at a question which combines continuous and discrete random variables, you might have a scenario where you have, kind of a large quantity of um, of objects. You might have like a barrel of 2,000 apples or something like that, and where you're kind of combining those two continuous and discrete random variables. You might have a case where like you're not, you're pulling apples out and you're not putting them back in, but at the same time, it's kind of there's 2,000 apples, so the trials are still kind of treated as independent for our purposes in year 12, because there's so many apples in there that the proportion isn't really changing, even though you're not putting them back in. So again, if you're more of a determined student, I would look into that as well. But we're not going to be going over it today because it's more of an advanced concept. All right. The last thing I want to go over for this slide is that for our Bernoulli sequences, our probability of success is given by P, and our probability of failure is given by 1 take P. We can also write this, sometimes you might come across it as Q. All right? So, obviously, our probability of failure is 1 minus P, because of course our entire probability of any outcome occurring is always 1, right? You might have a 30% probability of the car starting, and that means you have a 70% probability of the car not starting, right? All of our outcomes always are going to add up to 1. So of course our probability of failure is always just going to be the opposite of our probability of success. So that's where that comes from. All right. Now let's go through a quick test. What I would like you guys to do is pause the recording, have a look through this, and determine for yourself which of these are Bernoulli sequences. All right. So our first one is tossing a fair coin a few times. So this is a Bernoulli sequence because we have a discrete random variable. We have kind of two outcomes. We have a success and a failure, heads and tails. And our trials are independent, right? Our next option is trying to score a goal multiple times. So this is also a Bernoulli sequence, right? Or we can treat it as a Bernoulli sequence. So it's discrete. You can either score the goal or not score the goal. We have a success or failure situation. We don't have multiple possible outcomes. And presumably our trials are independent as well. I mean, I guess you could argue that, the chance of scoring a goal is going to change depending on how you're feeling or, where you are on the field or, other things like that. But for our purposes, we can just treat it as a Bernoulli sequence. Our third option is selecting people at random from a high school grade and noting their age. So this is obviously a random variable. However, it is not discrete because age is a measurement, right? So somebody can be, 15 years old, 3 months, 4 days, 6 hours and 14 seconds old. You know what I mean? Which means it's a continuous random variable, so it's not a Bernoulli sequence. Have a quick think about if we were given this information for part C, how could this question be changed to make it into a question where we would apply Bernoulli sequence maths? Pause the recording, have a think about it. So, what a question could ask, so that we would have to use Bernoulli sequence maths, is ask, what is the probability of somebody being, 13 years old, of course, if we're just considering, like, just years instead of, months and days and so forth, and not any other age at all. that is a situation where you might be using Bernoulli sequences. But again, it's kind of a gray area, and you really do need to think about it, and it will definitely depend on the question. All right. So this is how we represent our Bernoulli random variables. So of course we're going to have y, and the value of this of a failure is going to be 0, and this is going to be 1 minus p. The value of a success is going to be 1, and that's the probability of that is going to be p. Now let's get onto our formula for calculating the probability of a particular outcome. So, going back to this slide, if I asked you, say, what is the probability of getting heads 2 times when tossing a coin 3 times? So tossing a coin 3 times, and I say, what is the probability of getting 2 heads? Right? We are kind of asking probability x equals 2. What's this? Right? This is the question, this is kind of the most basic question you're ever going to come across for this topic. So if you get this kind of question, what you need to look at is our Bernoulli sequence formula. So we'll get into it in a second, but let's start with kind of each element of it. So the first element is our combinations, right? So what you will see in your formula is these brackets with n on the top and r on the bottom, right? This is what you see at the beginning of your binomial formula. So students sometimes get confused about how you actually calculate this and what it even means. This is actually combinations math. So if you're in specialist, you would have gone into a lot more detail on this in year 11. But if not, that's completely fine. You don't need to worry about it. We have a formula for calculating combinations, right? We also have a way of using Pascal's triangle, which in my opinion is kind of easier. And then you can also do it using your calculator very easily. So I'm going to quickly go through the formula that we have here. So what we have here is n, and now this exclamation mark is what we call in maths a factorial, right? F-A-C-T-O-R-I-A-L, factorial. So what this means is that we are multiplying that number all the way down to 1. So an example of this would be 4 factorial. 4 factorial would be 4 times 3 times 2 times 1. And then 7 factorial would be, have a think about it, pause the recording, do it yourself. 7 factorial would be 7 times 6 times 5. Can I count? No. 6, 4, 5, 4, 3, 2, 1. Right? So those are what our factorials are. So not too difficult to apply, but just something new that you likely haven't seen before. So this formula is not on your formula sheet. So what my recommendation is if you did not do specialist, I would recommend not using this formula just because it's just something else that you have to remember. And in my opinion, Pascal's triangle is kind of way easier. But again, if you learn how to do it using Pascal's triangle and you're really confused, then go back to the formula. Right? So these are kind of our two methods for calculating this NR without a calculator. So, as I said, in my opinion, using Pascal's triangle is a lot easier. So what you want to do here is use Pascal's triangle, so you can just quickly remember how to draw out Pascal's triangle. Remember we have 1, 1, 2, 1, and so forth. So what we're doing, that's not right. What we're doing is adding the previous two terms to get to our next term. So 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 1 is 2, and you can draw this on forever. So what we are doing is using Pascal's triangle. I'll do the last row down here. Using Pascal's triangle to actually find our n combination up here. So again, I would definitely study this in more detail. I'm just going over it quickly now in case you have forgotten it. So what you need to do is use this, right? So we're going to have n rows and the r position, right? So as an example of this, if we had 3C2, what we need to do, we can either use our formula, right, and we can have 3 factorial over 2 factorial, 3 minus 2 factorial. Or what we can do is go to the third row of Pascal's triangle. So our third row is going to be here, right? To know which row of Pascal's triangle you're looking at, what you want to do is look at kind of the starting number. So our third row, we know it's our third row because this number, our second number along is 3. So down here, this is going to be our fourth row, this is our second row, and so forth. So you want to look at this number here, and you're going to start with that row, and then you're going to go to position R. So our R value here is 2. So we want to go to the second position, right? So we're going to go to our third row and then count over to our second position. So the one kind of quirky thing to remember here is that with Pascal's triangle, we start at position 0. So this 1 here is actually the 0th position. Then this 3 is our first position. First, 0th. And then this is our second position. So this is going to be equal to 3, right? Because this is our number here. So going to our third row, our second position, the number is 3. Again, that was a very quick rundown. If you are left confused by that because you didn't go through it in enough detail in class, I know a lot of schools kind of don't. Don't worry. Either kind of go and watch a video about it on YouTube or something like that, or just make sure you do a lot of practice. I won't go through it anymore today just because it is kind of more of a, I guess, like a base level concept, and I want to focus more so on like the actual concepts in the maths and some more examples. But yeah, definitely go and do some more work on that if you're feeling a little bit confused. Just remember, using Pascal's triangle, what you want to do is go to the nth row. You know what row it is by looking at the number that it kind of starts with. And then you want to go to the rth position. So the 1 is always the 0th position, So always starting with 0 and then moving it across from there. So in 3 combination 2, which we just did, we went to the third row, which was here. Then we went across to the second position, so we went to the 0th, first position, second position, and the number that we landed on was 3, meaning that our answer here is 3. All right. And then there are also a few other things you need to remember about Pascal's triangle. And these that you need to remember are primarily for more complex questions. So these are going to be for ones where you need to find the n value. So we haven't gotten into that yet so far in our lecture today, but jot these down if you haven't already. So a lot of questions are going to ask you to just find, like, what's the probability of getting 2 red marbles, something like that. But in some questions, they're going to ask you, how many trials do we need to conduct to guarantee a certain probability of getting 2 red marbles? So, if we want a 90% probability of getting 2 red marbles, how many trials we need to conduct? So where n is our unknown instead of the probability, what you're going to need to remember is these combinations, right? Because you don't know what n is. So you're going to have like n, you might have 1 or n0 are the most common ones, right? So obviously without knowing what row it is, you need to be able to figure these out, and you can't put them on your calculator because you can't just put like n on your calculator. Your calculator does not know what that means. So what you need to remember is that looking at any row, our first position for n1, our first position is always just the number of the row. So for our second row, the first position is 2. For our third row, the first position is 3. For our fourth row, the first position is 4. So for this one, this is always just going to be equal to n. And then our 0th position for any row is always 1, right? 0th position, 0th position, 0th position. Always 1. So just jot these two down. Jot these two down in your notes and make sure that you remember those. Again, for questions where n is your unknown value. Alrighty. Again, if you're confused about what I'm talking about there, just jot them down and I'll give more of an explanation when we get into those kinds of questions. I just wanted to mention it now here that we're doing Pascal's triangle. Alright. And then, of course, if you need to find a combination when you are in a calculator exam, usually you don't need to because you're not even using the formula. You're actually just using, like, BPD or like stat or something on your calculator. You're just kind of popping the values in. You're not using the formula. But if you do, there'll just be a certain few buttons that you need to click on to get to it, depending on what brand your calculator is, what model it is. Usually you need to go to your usual menu, run, and then go into like options, probability, and then combinations or something kind of along those lines. But make sure you figure that out before you get into your exam. Alright, so this is the formula here for our Bernoulli sequences. So this is the combination section that we were going on about just there. So remember, to find the probability of x, we're going to have the number of trials x for our combinations, p, remember p is the probability of success, to the power of x, and then our probability of failure, which is 1 minus p, to the probability, to the power of, that should be n minus x, sorry, to the power of n minus x. Alright. And then this down here is just our formula for combinations for this first part up here. But as I said, use Pascal's triangle if you're comfortable with it. In my opinion, it is just far easier. What we have here is just kind of a quick example of why this binomial probability formula works, right? So if you have a look here, we have rolled a dice 3 times, and we have let x be the number of threes observed. So, where t means we got a 3, and n means we didn't get a 3, you can kind of see on the table on the right hand of the slide how this worked out for us. So, as you might expect, the probability of rolling 3 threes, as you can see up the top, is going to be the probability of rolling 1 3, which is going to be 1/6, right? Because we have like 6 numbers on a dice, and one of those is 3, to the power of 3. And the probability of getting 2 3s, right, is encapsulated by these 3 different outcomes here. So you can get a 3, and then not a 3, or a 3, then some other number, then a 3, or some other number, then a 3, then a 3. So these are the 3 kind of possible ways that we could get 2 3s, right? Then for each of these, of course, x is equal to 2, because we have 2 3s. And then, of course, for each of these outcomes, right, the probability of each of these outcomes occurring is going to be 1/6 times to the power of 2, right, because we have a 3 and a 3, so the probability of getting a 3 is 1/6, so we're going to have 2 of those, and then 1 failure, because we're going to have one number other than the 3. So the probability of each of these outcomes occurring is this part on the purple here. Now, of course, because we have 3 of these separate outcomes, we have TTN, TNT, and then NTT, we're going to have 3 of these altogether. So as you can see, this pattern continues. So for these top and bottom ones, where the order, or we can only have one outcome, right? Because we have TTT or NNN, right? We don't have a number out here. We just have 1, because there's only one outcome. But where we have 3 outcomes, we have a 3 out the front. So what this essentially shows is our Bernoulli sequence formula. So as you can see here, we have P to the power of our number of successes, R, and then Q to the power of n minus r, which is going to be 0, right, because all of our outcomes are t. So this is, of course, 1, so we just have p to the r, right? And our combination is C3C, which is just equal to 1. And then in our next row, we have C3, we have 3C2, right, which gives us 3. So as you can see, our combinations, determine the number out the front, and the reason why the kind of our combination number increases in the middle here is because this is when we have multiple outcomes, right? So again, this isn't something that you, I guess, need to kind of memorize. It's more just to help you understand it with how our formula actually works and like why it works, right? All right. So let's get on to a simple example. So here we need to find the probability of obtaining exactly 3 heads when a coin is tossed 6 times correct to 3 decimal places. So let's have a think about what information we know, right? So we want the probability that x equals 3, because we want the probability of obtaining exactly 3 heads. the coin is tossed 6 times, so we have 6 trials. And let's think about our probability of success and our probability of failure, P and Q. So P, probability of obtaining 1 head, is going to be 1/2, right? Because it is a regular coin, right? And then of course Q is going to be 1 minus P, or also 1/2, because that's going to be the probability of getting tails. Alright, so let's go through our actual our answer. So, as you can see, popping in all of those values into our formula, right, we are going to have N, which is 6, R, which is 3, and then P to the power of R, so half to the power of 3, multiplied by Q to the power of N minus R. And this gives us 5/16. One more other tip that I would have for you guys when you're practicing Bernoulli sequences is to make sure that you are familiar with multiplying fractions, right? Because of course, obviously, if you are doing this without a calculator, which you most likely will be, if you're using the formula, then you want to make sure that you are able to apply our power to each of the brackets and then multiply. So remember, just as a quick reminder, if you want to multiply 2 fractions, say A on B and C on D, all you need to do is combine the top and combine the bottom. So you're going to get AC on BD, right? And that's all you need to know. And then of course, if you have a fraction, say M over N to the power of A, remember that power is just applied to both terms. So M on A and N on A. So just some simple index laws, fraction stuff you would have learned in year 10 or year 11. Alright, now let's get on to kind of the relationship between Bernoulli random variables and binomial distributions. So, remember, a Bernoulli random variable is where we can describe the outcome from a Bernoulli trial, right? So if X is the number of successes in N Bernoulli trials, each with a probability of success P, it's essentially just saying if we just have our Bernoulli trials, our Bernoulli sequence, right, you know, with X, N, R, P, the values we've been learning about, this means that we have a binomial probability distribution. So a Bernoulli sequence is going to have a binomial probability distribution. What does this mean? Remember, a binomial is where we have 2 numbers, right? Binomial. So I'm going to show you what this looks like, right? So the binomial probability distribution is different for values N and P. Right? So the probability of guessing MCQ or multiple choice questions with a success rate of 0.2 and 0.5. So as you can see here, the probability of guessing multiple choice questions with a success rate of 0.2 is here, and 0.5 is here. So, now we want to get into how to calculate the expected value and variance for binomial random variables. So, it's a similar concept to what we went over with our statistics revision, but it's a little bit easier here. So for our expected value, all we need to do is multiply the number of trials by the probability of success, N by P, and our variance is going to be NP, or our expected value, multiplied by our probability of failure, or Q, or 1 minus P. So, these are on your formula sheet, and you don't really need to worry too much about how they got it, but you might be able to recognize some similarities between these formulas and the ones we went over at the beginning of the lecture. So, in a quick example here, if we have a question having 4 possible answers. A student guesses the answers to all questions. Let X be the number of correct answers. Again, pause the recording, have a go at this yourself before you go over the answer. Our first question is, how many will P be expected to get right? So we want to find the expected value. Remember, this is a binomial distribution, right? So we know that our expected value for a binomial distribution is going to be equal to NP. Our number of trials is 50 because he has 50 opportunities in every single question for a failure or success, right? So our failure is getting the wrong answer, success is getting the correct answer, so he has kind of 50 opportunities to either get the wrong or right answer. And then P is going to be 1/4. Right? Because we're asking how much is he expected to get right. If there's 4 answers to each question and he's just guessing, he has a 25% chance of getting the right answer. Right? So 50 divided by 4 is of course going to be 12.5. And then to find the variance, remember our variance for a binomial distribution is equal to NP, 1 minus P. So we'll just apply the formula from here, and I'll show you guys the nice typed of answer. So of course, applying our formula, we're going to get 50, which was 50 multiplied by 1/4, which was our NP from up here, multiplied by 1 minus P. So 1 minus 1/4, which is 3/4, and this gives us 75 on A. Again, make sure you're practicing with multiplying those fractions together so you can do this kind of stuff without a calculator. Alright, our next section is on finding the sample size for a binomial distribution. So, this is going back to what I was talking about when we were going over Pascal's triangle, and I was kind of saying, this is what you need to remember if you're ever asked a question where n is your unknown rather than the probability. So, as I said before, make sure you jotted those Pascal's triangle rules down, and then we'd explain more of the context when we got to this section. So, finding the sample size questions are kind of common, complex, familiar type exam questions, maybe even complex, unfamiliar if they add a level of complexity to it. What you'll typically be asked in these questions is, what does n need to be for our probability to have this, to be this certain amount. So, for example, how many lotto tickets to buy to ensure a 95% probability of winning, right? So, in these questions, what you're going to know is you're going to know P. That's going to be known, right? You're going to know the probability that X equals or like is greater than or less than or so forth. A certain value, you're going to know that. What you're not going to know is n. You're going to need to find n. So for these questions, what you need to do is apply your binomial probability formula, right? So you're going to have probability that x equals r, and then you're going to have your formula, n, r, p, so forth. That stuff we were doing before, right? So that's what you want to apply here. Of course, you're going to know your probability, you're going to know your p-value, and then what is going to happen, and we'll go through an example of this, but what is going to happen is most likely you're going to be able to get rid of this n here, right? Because obviously we have kind of two n's. We have the n here and the n here in our formula. So chances are you're going to be able to get rid of the n here by applying those rules that I was talking about when we were going through Pascal's triangle. And what you'll end up doing is solving for the n up here. So get rid of this n, then your only unknown will be the n up here. And then what you'll be able to do from there is use log laws to solve for this n, right? Because what you're going to get is you're going to get a certain number equaling q to the n minus r. Remember, whenever you have an unknown in the exponent, or like up in the power, going back to the beginning of the year, beginning of unit 3, what you want to do is use log laws to solve for that. So you can either pop a log on both sides, or you can use that quick little conversion, which is the first formula in your QCEE formula sheet under the logarithms heading. Again, we're going to go through an example of this in a second, just in case you're confused, but I'll quickly run over that procedure again. So remember, when you have a finding the sample size question, what you're going to have is you're going to know P, you're going to know the probability, and R, of course, but you're not going to know N. What you want to do in these scenarios is put all the values you know into our binomial probability formula. What you're then going to be able to do is get rid of this combinations part by using those rules that I was talking about with Pascal's triangle, and then solve for this n up here using log laws. So let's go through an example. So here we have the probability of scoring a goal is 0.48. So I'm just going to quickly jot down the information that we know as we go through it. Remember, if you are familiar with this kind of thing, or you just want to have a go, make sure to pause the recording and have a go. But I'll just go through the solution now. So we know that from this, P equals 0.48. What is the least number of shots that must be played to ensure that the probability of winning at least once is more than 0.95? So we know that the probability of winning at least once, we want this probability to be more than 0.95. So what we need here is a strict inequality. If you're unfamiliar with what that means, a strict inequality is these ones, where we don't have the equal sign as well. And then kind of a regular or like a weak inequality is where you have these ones. So because our probability needs to be more than 0.95, it can't be equal to 0.95, it has to be more. We need that strict inequality. And then we'll get on to the second part in a tick. So let's start off with this first part here. So of course we know that this is a finding the sample size question, because we know we're given P, we're given the probability, we're given R, but we don't know N. What is the least number of shots that must be played? This is N. What is N? Right? So remember, what we want to do is you want to apply our binomial probability formula. Now, there is actually a trick to this that you need to make sure that you remember for these questions. So, starting with what we had up here, we want the probability that x is greater than or equal to 1, and this probability needs to be greater than 0.95. Alright, so let's just say that we apply our binomial probability formula, like our nr in brackets, and then our p to the r, and our 1 minus p to the n take r, that stuff, right? Say we apply that, and we just put it, in here. So we want the probability that x is greater than 1, so we're going to need to start with probability that x is 1, and that's to be greater than 1, so we need to go probability that x equals 2, and then 3, and so forth. So we kind of don't really have a limit here to all of these probabilities that we're putting in. We don't know yet, right? So, of course, we don't know the limit, limits. We can't physically do this. And also, even if we did know the limit, we wouldn't want to put in a bunch of these separate formulas, right? It would just take way too long. It would be way too much effort. We want to avoid effort, right? So there is actually an easier way to do this, which I'm sure you can see already. And that is to use our 1 minus trick that I have right here. So, remember, usually when we are finding probabilities, if you kind of have this probability where you have x being greater than 1, you can just consider that this is going to be equal to 1 minus the probability that x is equal to 0. Because if x is greater than or equal to 1, the only other thing that it can be is 0. And our total probability, remember, is always 1. So, if we apply this, this means that we only have to put in our binomial probability formula for that one probability, x equals 0. And this makes things a whole lot easier. So make sure that you remember that, right? When you're applying your unknown sample size question, make sure you remember to use the 1 minus trick. Alright, moving on. So, let's get back to our first line that we have up here. So we have the 1 minus probability that x equals 0, and this has to be greater than 0.95. Right, I haven't shown the working here, but I'm just going to quickly do it off to the side here. So if we have 1 minus the probability that x equals 0, right, I'm just going to quickly pop in our values into the binomial probability formula and quickly show you how those kind of two equations that I gave you when we were going over Pascal's triangle can be applied right here. So hopefully you jotted those down. If not, we'll go over them again right here. So let's apply our formula. We're going to have n, right, which we don't know yet. R is 0 in this case. P, so P is 0.48. That was given to us in the beginning of the question. Remember how we wrote it down? The probability of scoring a goal is 0.48. To the power of R, which is 0. And then 1 minus 0.48 to the power of n minus r, which is 0. So this is what we have on the left-hand side over here. Now let's just go through and simplify this. So, let's start with our combination. So, remember those formulas I was going through before? If you have row n and the 0th position, this is always going to be 1. And if you have row n and the first position, this is always going to be equal to n. Remember, we went through why that works with Pascal's triangle if you want to go back to that part of the recording. So, what we know that is that this is going to be 1. Anything to the power of 0 is also 1. And then, of course, we can just simplify this a little bit further. So we're going to now have 1 minus 0.52 power of n, get rid of that 0 there. And then from there, to get to this second line here, all we did is took this 1 over to the right-hand side. Alright, now let's continue on with the question. So, as I said, we've gotten to a point here where we have this n in the exponent, or like up in the power, and that's our unknown. So, remember what I said. Quickly pause the recording, have a think about it. How did I say that we could solve these? Remember, it is, I guess you can see it on the slide, but we use log laws, right? Because we have our unknown in the exponent. Going back to the beginning of Unit 3, we're using log laws. So, as I said, you can either apply a log to both sides, or you can apply that log conversion formula, which is that first formula on your QCEE booklet for logarithms. So here we logged both sides. We used log base e, which is ln, and then so we went ln, and then remember that rule where we can take the exponent out the front, and this is what we did here. So we got the n out the front, and then all we did is took that ln over to the other side and divided it. Now, one other thing that I really want to reiterate here is using inequalities. A lot of people get confused with using inequalities to solve equations. What really happens is it's quite simple in theory, but not in practice. Right? So, when you're using inequalities to solve equations instead of like equal signs, like we have here, the rule is you change the direction of the inequality if you multiply or divide by a negative. So, I'll give you a simple example off to the side here. If we had a on negative 3 is greater than 2. Solving for a here, what we would usually do is just take this negative 3 over to the other side, right? But because we are multiplying by a negative number, what we need to do is change the direction of the inequality, just like so. So we're going to get that a needs to be less than negative 6. So that's how we would use that in a simple example, right? But then, of course, if you are adding or taking a negative, you don't need to change the direction of the inequality. So if we had a take 3 is greater than 2, right? We could have a is greater than 2 plus 3 without any issues at all. Alright, so that's the basic rule. That's really all you need to remember about your inequalities, right? When you change the direction, it's because you are multiplying or dividing by a negative. So, simple in theory, right? There's kind of two issues that students usually come across with using inequalities. So, the first one is when you don't explicitly know that a number is negative. So we have a perfect example of this here, and that is what we did is we took this ln of 0.52 over to the side, right? And as you can see, the direction of our inequality changed. So ln of 0.52 is actually a negative number, and that's why we needed to change the direction of the inequality, right? So, as a rule, when you're using kind of logs with inequalities, make sure you remember this. So if you have the log of any number between 0 and 1, this is going to be negative. Right? So as you can see here, the log of 0.52, because we have the log of a number between 0 and 1, that's going to be a negative number. In fact, if you pop it in your calculator right now, you're going to get a negative number. So, even though there's actually no negative there, it is actually a negative number, which you need to be careful of. So again, make note of that, right? Okay, and then of course it's not equal to. We don't have equal to in here, right? We don't have equal to because if we have the log of 0, that is not a number. We can't find that, and the log of 1 is 0. So, yeah. Alright, so make a note of that, keep that in mind. And then the other scenario that I actually had a student have issues with the other day was using the null factor theorem with inequalities. So again, this isn't relevant to this question here, but just to make a note of this, if you ever have something where you have like, you know, x take 1, x plus 2 is greater than 0. You can't necessarily use the null factor theorem here like you would if it was equals, right? Because for this number, actually I'll change it to make it a better example. Actually, no, it's fine. For we need to change the direction of the inequality if you're multiplying or dividing by a negative. Classic example, log of a number between 0 and 1. The other example is if you're using, if you have two numbers multiplied, you can't necessarily use the null factor theorem when you have an inequality. Alright, this gives us our answer for n. I'll just quickly see what this actually gives us. So, this gives us that n needs to be greater than 4.58. So, this is the number you're going to get. Of course, you can only have a full number of trials, right? You can't have 0.58 of a trial. So, if you get an answer that has like a decimal place, what you want to do is in your like written answer, say like n must be at least 5, right? Because we need at least 5 trials. Okay, getting on to the second part of the question. So the second part of the question asked, what is the least number of shots that must be played to ensure the probability of winning at least twice is more than 0.95. So in this scenario here, we want the probability of winning at least twice being more than 0.95. So the only difference between part 1 and part 2 is the R value. Here the R value is 1 and here the R value is 2. So let's go through solving this. It's a very similar process, but what you can see here, I won't go through this in too much detail, but what you can see here is applying the exact same process. We actually need to have 2 applications of our binomial probability formula, and we actually end up with an n here and then an n in our exponents. And the reason for that is because remember our rule n1 equals n, so this value here is equal to n. So when we have all of these n's, you actually physically can't solve this by hand. Believe me, I tried. I remember getting one of these questions in year 12, just doing it in a textbook. I tried for like half an hour to get the answer without a calculator until my teacher told me that it couldn't be done and to give up. But if you do get one of these questions, what you need to do is pop this into your calculator. You should have like a solve function. So I have a Casio. Our solve function is called solve n, and you just put the equation in. So that is what you would need to do here, and just solve it on your calculator. Another way that you could do it instead of using the solve function is actually by graphing this as a function and then finding for what values it's less than 0.05. Whichever way you prefer. My calculator is kind of old and a little bit slow, so it's usually easier to kind of graph it than use the solve function, but if that confuses you and you have like a fancy new calculator, please use the solve function. Alright, so this is it for Bernoulli